So in this video, I'm going to show you how to solve the linear system of equations using the Gaussian elimination. Yeah. So remember, the first step was you start with your linear system of equations, and we wrote it as a matrix times a vector equals another vector. Yeah, ax equals b. Then with this ax equals b, we wrote this augmented matrix, which was simply writing a and then b next to it. And then we said that with this augmented matrix, we apply Gaussian steps, which I have not yet explained to you. So please be patient. Just believe me. You apply Gaussian steps until you arrive at a row echelon form augmented matrix, which we call here U and C. Okay. So let's rewrite those steps here. So we started with a linear system of equations. We wrote it as a times x equals b, or better yet, we wrote it as the augmented matrix a and b. So far these three steps, they are not really steps, it's just rewriting things in different formats. Yeah. But once we have this augmented matrix, which I write as a line b, we apply the Gaussian steps, which I will explain later. And we get this row echelon form U, C, an augmented matrix. So U is in row echelon form. So what does this have to do with solving x, which is what we wanted to do in the first place? You might be wondering. So the key is this one. The solutions to ax equals b are the same solutions as those of ux equals c. Let me write it down. In other words, the Gaussian steps have not changed the solutions x. So we are only changing the matrix A and the independent coefficients b. So we are applying Gaussian steps to that augmented matrix, and we are changing them. However, the solutions to the system are still the same. So the solutions to ux equals c are the same as the solutions to ax equals b. Okay? And why is that good news? Because the solutions of ux equals c are very easy to find. And this is because matrix U is in row echelon form. So there are three cases. So case one is if there is a unique solution, and it happens when all of the columns have pivot. So UC might look like this. Then we have zeros to the bottom and to the left of all the pivots, because they are pivots. And then we have other numbers which might be 0 or might be non-zero above and to the right of each pivot. And then we have the independent coefficients C. Okay? So this matrix, all of the columns have a pivot. This means that the rank of this matrix is 4 in this case. So the rank of the matrix is equal the number of columns. When this happens, the nullity of the matrix is 0. There is no null space. And when this happens, the determinant of the matrix is not 0. So this is not a singular matrix. Okay? So this is the case when there is a unique solution. So remember, so determinant of A is not equal to 0. So there is a unique solution, which is the inverse of A times matrix B. But we don't need to calculate the inverse. Okay? Thanks to this fact that the system UC is equivalent to the system AB, we can find the solutions directly. So how do we do it? We solve it by inverse substitution. So how does inverse substitution mean? How does it work? So we need to start from the last row, okay? Well, first, before I do that, remember that each column is associated to one variable, right? Remember, that's how we started all of this topic. So we wrote this system of equations as a matrix times a vector equals another vector, and each of the columns corresponds to the coefficients of each of the variables. Yeah. So let's say that each column has a name. The first column has the name of the first variable, the second column has the name of the second variable, and so on. So now, if you write this augmented matrix in the original form as a linear system of equations, the last row would be an equation that says d times x4 equals asterisk, where asterisk is some number. And therefore, x4 equals asterisk divided by d. So we have found x4. So using the last row, we find x4. Now, knowing x4, we can solve the next row, the third row. So why is this? Well, if you write the equation associated to this row, yeah, so this equation will be c times x3 plus asterisk times x4 equals asterisk. Of course, I'm using asterisks as these numbers, but in general, they are not the same number, yeah? Just don't be confused by this. So, for example, if this asterisk was a 2 and this was a 3, then this will mean that cx3 times 2x4 equals 3. Yeah, okay. But I'm just using asterisks. So then it means that by substituting the solution of x4, we can calculate x3, because x3 is simply equal to 3 minus 2x4 divided by c. We can solve for x3. Okay? Let me go back to asterisks so that I'm keeping this general. Okay, so we can solve x3. Now, since we know x4 and we know x3, we can solve the next row. So the next row says b times x2 plus some asterisk times x3 plus some number times x4 equals some other number. Since we know x3 and x4, we can solve for x2, right? Because we can move everything that is known to the right and then divide by b. So now we know x4, we know x3, and we know x2. So we can substitute them into the first row, because the first row is a times x1 plus some number times x2 plus some number times x3 plus some number times x4 equals some other number. So we can move all the numbers times x2, x3, and x4 to one side, because we have solved those. We divide everything by a, and we can find x1. So in this way, we can find the values of the 4 variables. Okay? So the summary of this procedure would be: start with the bottom row and work your way upwards. Great. Okay. Case number 2. There is no solution. When does this happen? This happens when some rows of U are all 0, but the corresponding independent coefficient is not 0. How would this look like? So this might look like this. So here I drew an example in which 2 of the rows of U are 0, but it doesn't have to be 2. It could be only 1, or it could be any other number bigger than or equal to 1. Yeah. So we have rows where everything is a 0. Yeah. And at least one of those rows has a non-zero number on the independent coefficient part of the augmented matrix. Okay. What does this mean? This means that 0x1 plus 0x2 plus 0x3 plus 0x4, so basically 0, equals this non-zero number. So whatever this number is maybe equal to k. Yeah, so 0 equals k. So if k is not 0, there is no solution to this system. So then we say no solution. Okay, so the system has no solution. And finally, the third case. So this is whenever we are not in the case 1, so not all columns have pivot, yeah? But we are not in case 2. No case 2. So we don't have 0 equals k. So we always have zeros. Whenever a row is all zeros, we have a 0 also in the right. Okay? So this is case 3. How would case 3 look like? Let me give you an example. So this would be an example of case 3. Why is it an example of case 3? Well, the third column has no pivot. Remember, this is not a pivot, yeah? Because there is a non-zero number to the left. So remember, the pivot for each row is the first non-zero number in the row. So for the second row, the pivot is B, yeah? And for the third row, the pivot is C, yeah? So this column doesn't have a pivot. So remember, this means that each of the columns is associated with a variable. So this one is x1, x2. This one is x3, and this one is x4. And we are not in case 2 because this number is 0. Yeah, even though all of these are 0, this one is 0. So we get 0 equals 0. So that's fine. We are okay. But we have a column without pivot. So what happens then? Then the variable associated with that column is a free variable. So we can give it any value. So normally we choose lambda. We normally use Greek letters, yeah? So lambda is any number. And now we can solve the other variables, x1, x2, and x4 by inverse substitution in the rows, starting from the bottom row and moving upwards. But whenever x3 appears, we leave it as lambda, okay? And this means that the solution will have a degree of freedom given by lambda, okay? So now we would do inverse substitution. So we can solve x4. So we have that c times x4 equals asterisk. Therefore, x4 equals asterisk divided by c. Then from this second row, we have that b times x2 plus asterisk times x3, which is lambda. So we leave lambda there. Plus asterisk times x4 equals asterisk. So we can solve for x2. But x2 will have a lambda there. Yeah? So we will have a lambda involved in x2. And then we do the same with x1 using the first row. So we find x1 using the first row. So how will the final solution look like in this case? So let me make up the numbers. So we know that, so let's write the solution x1, x2, x3, and x4. So we know that x3 equals lambda. And we know that x4 was asterisk divided by c, so that's some other number. Let's say that this was 3. Now we know that x2 and x1, so there will be a lambda involved in x1 and x2, right? So let's say this is 2 plus 3 lambda and 1 minus lambda. I'm completely making this up, yeah? Now, why don't we write this in vector notation? Equals this vector, yeah? We can do that. And this is equal to vector x. But look at this. We can group those numbers that are not multiplying lambda. So in this case, it would be 1, 2, 0, and 3. And then plus lambda times those numbers that are multiplying lambda, which would be minus 1, 3, 1, and 0. And now this is great because now we have the equation, the parametric equation of a line. right? This is the parametric equation of a line. We have x0 plus lambda times some vector v, which is the direction of the line. So we are solving this system of equations geometrically by saying that the solutions span a line. So there are infinite solutions. Now, if instead of having one column without a pivot, we would have two columns without a pivot, then we would have two free variables. So we would have two parameters, alpha and beta. And therefore, instead of having the equation of a line, we would have had some vector plus alpha times another vector plus beta times another vector, which would be the equation of a plane. So clearly the number of free variables is giving us the dimension of the subspace of the solution for x, for vector x. Yes? So that is, if you think about it very carefully, that's why the number of columns without a pivot equals the nullity of the matrix. And it's related to the fact that the determinant of this matrix is 0. Yeah. In the case where there was only one unique solution, you only had one value for x1, let me make it up, one value for x2, one value for x3, and one value for x4. Yeah, which corresponds to having a single vector x, which is fixed. So we have a fixed vector x because there is a unique solution. Okay, and that's because there were no free parameters in case 1, because all of the columns had pivots. Excellent. So now you know how to solve the system once it's written in row echelon form. So the only question that I still need to tell you is how to do the Gaussian steps to transform the original matrix into row echelon form. And that's the next video.